Welcome back. Um, the inverse of a cycle. So like here I have a cycle of length r. The inverse of a cycle of length r. So here the cycle is a1, a2, dot dot dot, ar minus 1 ar, and the inverse of that is basically right now a1 is assigned to a2, a2 goes to a3, a3 is assigned to a4, right? So the inverse is basically the assignment is simply the opposite. So AR is assigned to AR minus 1, AR minus 1 is assigned to AR minus 2, and you keep going, and A2 is assigned to A1. So the arrows are being reversed here. So here the arrows goes to the right. Here the arrows but now if we reverse the arrows, so AR to AR minus 1, AR minus 2, AR minus 1 to AR minus 2, and dot 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 A2 to A1. So that's this one. And you can check that if you multiply them, you get the identity permutation. A transposition is a cycle of length 2. If I have a cycle, I can always express that as a product of transpositions. So this cycle here, 1, 2, 3, 4, 5, I can express it as a product of transpositions. And notice there is a specific way we can do this. So notice that I'm getting 1, 5, pairing up 1 with 5, 1, 4, 1, 3, and 1, 2. So 1, 5, 1, 4, 1, 3, 1, 2. So, and if I have this, then individually each one of them I can express as a product of transpositions. So the whole thing can be expressed as a product of transpositions. So the first one can be written as 1, 2, 1, 3, and 1, 6. This one can be written as 4, 7, and 4, 5. So again, we get a product of transpositions here. 1, 2, 3, 4, 5, we can also write this a little bit differently. That is, you say we can write 5, we can write 5 here, and then that is we can shift everything to the right by 1 unit. Then 5 would be here, and then 4 would be at the end here, right? So if I put 5 at the beginning, then everything will be shifted to the right. So then you can see that I'm getting 5, 5, 4, 5, 3, 5, 2, 5, 1. So that's another way of expressing the same cycle as a product of transpositions. So the last one here I have expressed the same cycle 1, 2, 3, 4, 5 as a product of transpositions again. So here I have 5, 4, 5, 2, 2, 1, 2, 5, 2, 3, 1, 3. So given a permutation, we can express that as a product of transpositions in many different ways. What is the inverse of a transposition? Well, a transposition is a cycle of length 2, so we know that it has order 2, and so as a result it is the inverse of itself. So if I have 3, 5, a transposition 3, 5, then if you multiply 3, 5 and 3, 5, you are going to get the identity permutation. So for example, notice that both of these cycles they fix all the elements except for 3 and 5. Now if we multiply them, they also fix 3 and 5. So 3 goes to 5 here and 5 goes to 3. So then this product takes 3 to 3. This product takes 5 to 3 and 3 to 5. So this product takes 5 to 5 as well. So we get the identity. So the inverse of a transposition is itself, and it has order 2. Every cycle can be expressed as a product of transpositions, so every permutation can be written as a product of transpositions. Like I said, if I have A1, A2, dot 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 AR minus 1 AR, that's a cycle. Then I can express that as a product of transpositions, A1 AR, A1 AR minus 1, dot 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 A1 A2. We can also express it as AR AR minus 1, AR AR minus 2, dot 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 AR A2, AR A1. Here's a lemma that I'm not going to prove, but if we express the identity permutation as a product of if we express the identity permutation as a product of transpositions, then the number of transpositions in the product will always be even. So if we express epsilon as the product beta 1 dot 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 beta r, where these betas are all transpositions, then r must be even. So if we express epsilon as a product of transpositions, then the number of factors will always be even. If a permutation alpha can be written as a product of an even number of transpositions, then every decomposition of alpha into a product of transpositions must have an even number of transpositions. And I can make the same statement with odd. So what we are saying here is that given a permutation alpha, I can express that as a product of transpositions in many different ways. But one thing never changes, which is how many, which is the parity of the number of transpositions. So if I express alpha as a product of transpositions, then the number of transpositions will always be either even or it will always be odd. So let's try to prove this. So let's say tau 1, tau 2, and tau k, and delta 1, delta 2, delta m, these are transpositions. Let's say sigma is a permutation, and sigma can be written as the product tau 1, tau 2, dot 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 tau k, and sigma can also be written as the product of deltas, delta 1, delta 2, and dot 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 delta m. Now, since sigma is equal to both of them, then clearly sigma times sigma inverse is 1. But sigma is tau 1, tau 2, tau k. Sigma inverse, well, I'm going to take sigma is also equal to the product of the deltas. So I'm going to take the inverse of the deltas. Now, the inverse of a product, we know that is the same as delta m's inverse multiplied by dot 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 delta 2 inverse, delta 1 inverse. But the inverse of a transposition is itself, so we see that the identity permutation is equal to tau 1, tau 2, dot 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 tau k multiplied by delta m dot 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 delta 2, delta 1. So notice that in the previous lemma we said that the identity permutation, if we express the identity permutation as a product of transpositions, then the number of transpositions would be even. So here the number of transpositions here is k plus m, so k plus m must be even. Well, if k plus m is even, then either both L and M are even, or both L and M are odd, right? So if L plus M is even, then either both M and L are even or they are both odd. So that pretty much proves that if I express alpha as a product of an even number of transpositions, then every decomposition of alpha into a product of transpositions must have an even number of transpositions. Again, we can make the same statement with the word odd instead of the term even. So a permutation that can be expressed as a product of an even number of transpositions is called an even permutation. A permutation that can be expressed as a product of an odd number of transpositions is called an odd permutation. The subset AN of even permutations in Sn is a subgroup of Sn. It is known as the alternating group of degree n. For n greater than 1, An has order n factorial divided by 2. That is, half of the elements of Sn are even, and the other half are odd. Well, the remainder of the slides are basically exercises, so this is it. This is the end of our discussion on permutations.